my name is Jason Doe, and this will be my short presentation on antibiotic resistance and our methods of combating it. First, I'd like to lead off on what antibiotics are. Antibiotics, or the original antibiotic, was penicillin. It was actually discovered by a Dr. Alexander Fleming, and what's cool about it was that he actually discovered it by accident. It's an accidental miracle, and to this day, it's actually contributed to being up there in creation such as the wheel or fire. It's just such a meaningful discovery because this is a discovery that basically stopped deaths from simple bacterial infections from day to day life. And it was hailed as a miracle. And it was funny because originally when Fleming found it, it wasn't a miracle at all. He actually just noticed that it just happened to kill the bacteria who was going on a plate. And it wasn't until a decade later when one of his teams who were working on it at the time finally were able to isolate it and turn it into a pill form, like something that was actually digestible as a modern day antibiotic. And this again meant that bacterial infections no longer meant certain death, and they've been prescribed ever since. Or basically after you get a root canal, or if you get a nasty, like a super deep cut that's just bleeding and you don't want to risk infection in it. But that's the thing, we prescribe it for so many things. And that is one of the bad parts of antibiotics is how they function. The term mutually assured destruction means killing of both sides no matter outcome of a war. And using antibiotic is basically nuking your whole digestive system with just killing every bacteria because antibiotics kill indiscriminately. And you may not think, oh, but I'm killing bacteria. Are we actually thrive on having good bacteria in our body? And the fact that you're killing all of this healthy bacteria that's actually helping you, promoting you, actually weakens you and can potentially open you up to other health risks and adversities. So that's the reason why probiotic supplements are also recommended during the time where you're taking antibiotics. But again, no matter what, we're also still looking for alternative for antibiotics on top of antibiotic resistance. And antibiotic resistance, for those who aren't aware, is basically when a bacteria mutates a gene that allows it to be resistant to bacteria. Basically, a lot of places describe it as, oh, it learns the gene or stuff like that. Bacteria, due to how fast they multiply, how fast they reproduce, actually have a lot of mutations, and one such mutation can give them the antibiotic resistance. And when this happens, they're the only ones to survive. So of course they move on, they replicate more, and you basically see this positive feedback loop where suddenly now you have a whole plate of antibiotic resistant bacteria. And it's actually been studied and shown that these antibiotic resistant bacteria can also pass this resistance on to completely different bacteria, not of the same strain. And that's like the actual scary part. And it's because of this that we do have like stronger strains of antibiotics to basically stop what we would know as a superbug. But there is a limit to what we have left, which brings us to basically what do we do? And I like to call them secret weapons of last resort, basically. So the first one that I found recently is something called DLRs, or drugs of last resort. Basically, these are pharmaceutical class drugs where they can be used, and again, as a last resort, but because the side effects are so severe and potentially fatal, they aren't used unless it is absolutely deemed necessary. And it's hard to make that decision because some of these side effects are blindness or severe hemorrhaging in the inside. So it's just, these are to just buy time, more likely, in an event of a death. Another is what I personally have been studying recently are molecular chaperones. And these are basically the proteins that help other proteins. They're the tool belt that the human body uses to basically help proteins function and fold. And for any of those who are in microbiology or biochem, you know that the shape of a protein after it's folded actually helps dictate what it can do. And lastly, as shown to the right here, are bacteriophages. These are basically specialized viruses that can be designed to kill certain bacteria. And what's cool about this is knowing how a phage works actually shows a lot of promise to how we can deal with cells and specifically bacteria, which are single cell organisms. So to start off, I'd like to talk about molecular chaperones. And basically, again, these are specialized proteins that just help other proteins function. So, as mentioned before, folding is super important. We basically want to make sure that proteins fold not only quickly but properly because misfolded proteins can cause aggregates. This leads to possibly amyloid formations, which is a completely different bag of worms. So basically, that is one of the main reasons how Alzheimer's happens. And one of my favorite ways that it's been taught to me was a molecular chaperone is a tool belt, like I said before. And it does a lot of things really well. And it's interesting because chaperones can help other chaperones, which in turn help other proteins. So it's proteins helping proteins, basically, which is really cool. And to go deeper is specifically heat shock proteins. So heat shock proteins, or HSPs, is how we call them. This is a lot easier. Are basically specifically class of molecular chaperones that basically deal with proteins under stress conditions, usually heat, hence the name heat shock. And these basically will either help a protein fold back because when you heat up a protein, it denatures. It'll either help it fold back into its original shape if it's not too far gone, or more importantly, it actually can also just fully degrade a protein away, preventing it from ever misfolding in general. So if a protein's just too far, like if it's unrepairable, it'll just basically tag it or just get rid of it in its entirety and just basically help, and the body will then recycle its nutrients to form other proteins. And of note for the heat shock proteins, I'll be covering both HSP90 and HSP70. So first off is HSP90, which is a heat shock protein found both in humans and bacteria, with, and most importantly, there is actually a very small difference between them. That actually makes it a really good drug candidate because as long as they're like basically heat shock proteins exist everywhere in all organisms, but the fact that there has been an identifiable difference basically allows us to design a drug that specifically only targets the bacteria version. And this heat shock protein actually controls the gene that, or the enzyme that leads to the eventual drug resistance in bacteria, which is even better. So we can actually target this HSP90, basically figure a way to shut it off with either a small molecule or any other mechanism. And this actually will then stop the formation of the drug resistance from happening. What something else it can do is basically this also helps it fold. What is it? Helps protein fold, but also helps them strengthen. So even if we can't stop that drug resistance, we can actually weaken the bacteria. So a weak bacteria is a more easily killable bacteria and a more easily treatable bacteria. So it's a win-win. Next up is HSP70. So again, this is another heat shock protein, but this actually is more important in basically keeping the protein stable. And what's really cool is that HSP70 is known to have co-chaperones. I think it's basically DNA K off the top of my head, and basically these help HSP70 in binding to proteins. And for the basis of this, if heat shock proteins are your tool belt, think of the co-chaperones such as the DNA K as tools in that tool belt. And this assistant binding is also really interesting because if we can actually target this function, we can basically turn off certain protein folding, which again helps to target the bacteria we're actually working with, because HSP70 alongside HSP90, there are slight differences between bacteria and humans. So really cool research. And next off, also really interesting, are bacteriophages. So I love this image from Chris Guzar. I think this is from one of their posters. But basically, these are what a virus is, basically. And how viruses work by basically injecting their own DNA into a cell and forcing that cell to recreate more copies of it and then lysing the cell open. So basically busting open the cell and then spreading more of the phage around. And this is really interesting because phages are actually cell specific. They only target one type of cell And when, if ever discovered or ever basically genetically engineered, we can actually make bacteriophages that kill target bacteria. So basically, the common cold, I forgot what it's called, the actual germ name of the common cold, but stuff like that, or like the common flu, stuff like that. Basically, we can actually target these specific bacteria and just kill them without killing anything else, because again, they're genes, cell specific. And basically, the last conversation I want to have with you is, will it work? We know drugs of last resort work because again, they're of last resort. There have been cases where, with no other option, patients had to resort to these basically on their deathbed just to buy a little bit more time for final goodbyes and the like. Or if they do work, they leave everlasting damage on the patient. For HSPs, I'm currently working in a lab, but I know research is still ongoing. It's more of identifying the actual drug targets and just getting more data, because there is a severe lack of data on how the binding or how the interactions actually work on a molecular level. And lastly, bacteriophages are the ones that show the most progress due to actually us being able to finally start designing genes and in turn actual phages. And because of this, and the actual neat part is, if a bacteria ever does try to form a resistance or mutate resistance against viral infections from bacteriophage, it has to lose some antibiotic resistance. So we can basically force it into this catch-22 where we can effectively trap the bacteria and force it to, and be able to treat it one way or another. And that's my, I guess, like my short presentation on antibiotic resistance and what we're doing to combat it. So I just want to say thank you, and here's more excited. Most of all, the paper Two Distinct Classes of Co-Chaperones and Kuzgas are my favorite sources. Bye bye.